An artificial dielectric made from an array of conducting spheres demonstrates how polarization of media gives rise to the properties of a linear dielectric. When the region between electrodes is filled with a dielectric material, the capacitance is increased. This increase is due to polarization of molecules of the material. We form an appreciation for how this happens by replacing the molecules with macroscopic spheres suspended in air. This artificial dielectric is composed of what we can think of as molecules that are actually essentially perfectly conducting spheres. Each has radius r, and they're in a cubic array with spacing s. Application of voltage to the electrodes results in the spheres acquiring positive and negative surface charges on their poles. In addition to the uniform field, due to the applied voltage, the field outside the spheres also includes the dipole fields from the array of spheres. The spheres, like the molecules of a material, are polarized by an applied field. The artificial dielectric is composed of an array of ping-pong balls with conducting coatings. We're going to measure the effective permittivity by measuring the change in capacitance as the array is placed between the plates of this plain parallel plate capacitor. The cage is grounded for shielding and to keep us from touching the bottom electrode. It's driven to 400 volts RMS at 250 hertz by this transformer, which is itself driven by an oscillator and amplifier. Here's the top electrode. To avoid fringing effects, only the charge induced on this central section will be measured when we measure the capacitance. Here's how the dielectric is inserted between the plates. Before balancing the bridge, we remove the array of ping-pong balls. We've already set the driving voltage to about 400 volts RMS. Here are the resistors in the two upper legs of the bridge. They shunt the scope differential amplifier. So the scope signal is the voltage V sub 0. The balancing capacitance, C2, is here. This is the capacitor, C1, which is there for fine-tuning. We can balance the signal with this capacitor. So we tune C2 to null the bridge voltage, and C1 to fine-tune the null. We're ready to insert the artificial dielectric. As the array is inserted, the bridge becomes unbalanced, indicating that the capacitance is changed. We measure a voltage of 135 millivolts peak. Remember, what we predicted was a change of 133 millivolts peak. The agreement is perhaps better than we should expect. Has the capacitance actually been increased by the insertion of the spheres? Let's try the experiment again. We can see that it has by looking at the balancing capacitor. Here, the array is out, and we balance the capacitor. Now, we insert the array. Note the position of the tuning capacitor plates. If the capacitance has been increased, to balance the bridge, the knob must be turned so that they have greater area of overlap. The balancing capacitance is increased. So the artificial dielectric does increase the capacitance of the plain parallel capacitor.